Okay, there is only one section left to be covered in this chapter, chapter 10, and that deals with the oxidation and reduction of organic compounds. So, unlike the case of general chemistry, where you can assign oxidation states to particular elements in a based on the location on the periodic table, like manganese, chromium, etc. In organic chemistry, there is a little more qualitative way to do it, and that is based on the number of attachments of more electronegative elements that you have to a carbon atom, or the number of hydrogen atoms attached to a carbon. So let me illustrate this with a couple of examples. For instance, if we have a compound with this structure, so we can assign oxidation state to each one of the individual carbon atoms in this way. We will say for each attachment to a hydrogen, we will add -1. So that is for each hydrogen. For each attachment to oxygen or some other more electronegative element, we will add 1, and that will be for each oxygen or halogen or nitrogen. And for each attachment to another carbon atom, we just add 0. So attachment to another carbon atom, it will give you 0. So that means that the oxidation state for that particular carbon atom will be what? We have 3 attachments to hydrogens, so that will be -3. That carbon atom there, we have 2 attachments to oxygen and a couple of attachments to carbon, so the number will be +2. And then the next carbon atom, this one will be -2, that one will be -2, and this one here will be -3, right? And let's say that I perform a reaction. It could be a reaction with lithium aluminum hydride followed by H3O plus, and that is going to give me the corresponding alcohol. Well, obviously, the first carbon atom, this one, and that one, they will end up with the same oxidation state. The only carbon atom that change the oxidation state will be that one there, right? And what will be the new number for that particular carbon atom? Well, we will have 0 for the attachments to the neighboring carbon atoms, and then we will have -1 for the attachment we have to a hydrogen, and +1 for the attachment that we have to the oxygen. So the new oxidation state for that carbon atom will be 0. So we are going from a +2 to 0. We are going from a bigger number to a smaller number. So that's why we will say that is a reduction. Easy enough? Let's say that you have now this compound. You have this compound that I am reacting with Br2 and light, and I get this. Is that a reduction, an oxidation, or none of the above? Well, here I have 3 attachments to hydrogens, while in the product I have 2 hydrogens and a bromine. Bromine is more electronegative than carbon, so certainly that would have been an oxidation, right? It's an oxidation because I end up with a carbon atom that is at a higher level of oxidation than what I started with. So if I go in a series, let's say that I go from methane to CH3Cl, chloromethane, then I go to CH2Cl2, and I go to CHCl3, and then I go to carbon tetrachloride. So that will be a sequence of oxidations, right? Chloromethane is more oxidized than methane. Dichloromethane is more oxidized than chloromethane, etc., etc. And carbon tetrachloride will be the most highly oxidized because we have 4 attachments to chlorine. So here we have another series of oxidation. You can go from propane, you can go to propanol. Now we have one more attachment to a highly electronegative element, oxygen. Then we go to the formation of propanaldehyde. That is an aldehyde because we have a COH group. And then finally, we can go yet to one more oxidation state, higher, and we form propionic acid. That is the acid that is responsible for the smell of the Swiss cheese, propanoic acid. Let's see one more, another couple of examples. Here we go from methane, reaction with chlorine and light. So that will give me chloromethane, so that is an oxidation. And the other example we have here, chloromethane, you react that with magnesium in ether. So there you will form the Grignard reagent. You will form CH3MgCl. And then in the second step, we react that with H3O plus and we form methane. So the overall transformation of chloromethane into methane, that will be a reduction. There are some very good exercises in OWL. You know, sometimes in OWL, when they teach you a certain thing, at the beginning, you will have some pages that they say, read this page before. And what do we do normally? We skip that, right? Well, this time, please read that initial page because it's there is some very useful information. Before I go, let me just show you some tricky cases of oxidation and reduction. Let me just erase a little bit here. Somehow I cannot erase those. There, okay. Okay, there. So let's say that you have a reaction that you have a carbonyl compound and somehow you manage to form a diol like this. Is that an oxidation, a reduction, or none of the above? Well, the central carbon atom in the starting material is attached to 2 oxygens, and the central carbon atom in the product is also attached to 2 oxygens. So this is neither an oxidation nor a reduction. Another tricky case, let's say that you have an alkene and I perform a hydration, and it doesn't really matter if I use the Markovnikov process or the non-Markovnikov. In either case, I will get the same product, hydration, and I will get that. Is that a reduction oxidation, or none of the above? Well, because one of the carbon atoms is getting oxidized, is getting more attachment to oxygen, and the other carbon atom is getting more attachments to hydrogen, right? So while one of the carbons is getting oxidized, the other one is getting reduced. So the overall transformation is neither an oxidation nor a reduction. Okay, so in the following installments, we will get started with chapter 11. So I will assume that you are reading the textbook